Welcome to the Lifting Solutions KeBond webinar session number 2. Today we will discuss KeBond success in corrosive applications, learning in abrasive applications, and other practical insights for your well. My name is Ryan Rowan. I am our Director of Technical and Application Support, and I will be discussing field application initiatives with our innovative coated rod product KeBond, followed by an open question and answer session where I will be joined by Lonnie Dunn, our VP of Manufacturing and Engineering, along with Chad Giesbrecht, our Director of Fleet. Today, we are going to do a high-level recap on our initial webinar in case you missed some of the highlights. From there, I will provide a high-level overview of the engineering, manufacturing, and servicing advantages of KeBond. This leads into an application discussion focused on the design and recommendation of KeBond in rod-driven systems. I will update you on our current field experience overall, and then focus on a few of the case studies with real results before ending off with a question and answer session. Our first webinar in the KeBond series focused on our innovative solutions to enhance corrosion protection in rod-driven systems. Corrosion and fatigue are significant contributors to rod string failures. Barrier coatings have been used in industry for many years as a method to prevent corrosion on everything from marine, oil and gas, aerospace, automotive, chemical processing, and electronics, to name a few. They act as a physical barrier between the corrosive environment and the substrate material. Our initial coated rod product is called EthiFlex. This is HDPE, high density polyethylene, unbonded product that has its own unique advantages. It's strippable, it has a salvage value. Flex in the name indicates it is flexible to be taken off. And disadvantages in service weight limitations, low to moderate oil resistance, and low temperature resistance with a maximum of 40 degrees C. KeBond is our next generation of bonded polyketone material, which provides different, somewhat inverse advantages. It's bonded. It has increased service weight limitations, oil and temperature resistances, and disadvantage, it's bonded, it's not strippable. Worn sections need to be replaced. Alternatively, a worn and compromised string can be redeployed in a non-corrosive application. Again, somewhat of a recap, I have a couple slides to cover KeBond engineering work, manufacturing processes, and servicing validations. KeBond has several unique advantages and disadvantages outlined in our initial design requirements. We were looking to improve servicing depth and temperature limits on our coated endless rod product and needed to overcome bonding limitations of thermoplastics to the steel rod surface. Once bonded, this coating cannot be economically removed. Our initial KeBond conceptualization included evaluation of many material and bonding methods before choosing polyketone for its ability to meet the predefined design requirements. Prior to entering field trials, our engineering team did an extensive evaluation of KeBond, including detailed testing of the mechanical properties, fluid resistance, gas resistance, wear resistance, and servicing requirements. Additional details for each test program are shown in the table. In early 2023, Lifting Solutions custom designed a manufacturing facility capable of producing 150,000 meters or 500,000 feet per month of coated product. This line included extensive instrumentation, automation, monitoring, and traceability of our build quality, which was further supplemented under our ISO 9001-2015 quality management system. In addition, this manufacturing line is capable of experimenting with different coating materials and thicknesses as we continue to evaluate the future potential of barrier coating in the oil and gas industry. Extensive product validation was completed to confirm KeBond's ability to meet serviceability requirements outlined in our design requirements. This included bond and gripper push-out testing on new product and after thermal and fluid exposure. We tested several common rod clamps and fishing tools which were approved for use with KeBond. Evaluation of low temperature product handling and full-scale service equipment trials with new rod and diesel lubricated rod resulted in validation of serviceability as illustrated on the slide. This gave us confidence to begin Canadian field trials in the second half of 2023. With critical engineering, manufacturing, and servicing components completed, we started searching for KeBond applications that met predefined criteria, centered around short runtime rod failures in applications with repeated corrosion-initiated fatigue failures. Corrosion pits act as a stress riser or concentration point and must be prevented at all costs on a rod string through either corrosion, inhibition, and/or barrier coatings. Alloyed metallurgies including chromium, molybdenum, and/or nickel will reduce corrosion tendencies on the metal rod, but it will not be eliminated as it is through the use of an intact barrier coating. Amplified by the stress concentration of a corrosion pit, the main contributing factors to rod string fatigue are cyclic bending, which is the compressive and tensile cycles experienced on every PCP revolution. The degree of severity is a function of the wellbore directional survey, and once the well is drilled, this cannot be changed. Axial load fluctuations are low in PCP applications compared to reciprocating applications. They are driven by subtle variations in the discharge pressure of a PCP caused by the changes in the fluid emulsion being produced. Slugging of oil, water, sand, or gas will have an effect on the discharge pressure of the pump. Discharge pressure is directly related to both axial load and torque fluctuations in a PCP. Torsional fluctuations are defined by the period and the amplitude, which can be difficult to measure in the field but are typically between 15 to 30% of the total torque when adequate data acquisition equipment is in place to accurately monitor this. The final stress in a rod-driven system is currently less understood, but Hertzian stress is a contact stress that occurs when two metallic bodies come into contact, causing residual stress at the contact points. To further investigate the contribution of corrosion and pitting, we developed custom fatigue testing equipment to evaluate cyclic bending, tensile, and torsional loading. The test program confirms the importance of corrosion pit prevention, with early results indicating 1/6 to 1/3 of the fatigue life evident on a rod string with a simulated defect of 25 thou. This also confirmed initiation and propagation of the fatigue cracking originating from the base of the pit or the defect. An expanded test program continues to evaluate the effect of stress risers on rod string fatigue life. We are focused on finding applications with corrosion-initiated rod failures. Lifting Solutions utilizes CFIR PC Pump software to provide an in-depth application analysis which provides detailed insight into our KeBond applications. CFIR uses wellbore geometry and curvature components along with the fluid properties, operating conditions, and equipment specifications to analyze rod torque, axial load, maximum effective rod stress, and different pump metrics including pump pressure loading, differential pressure, and pump torque. There is a lesser known auxiliary analysis module that is fairly basic, but it can be used to estimate and visualize rod string fatigue life under simulated conditions. This module adds the ability to iterate both the corrosion factor and torque fluctuations. These inputs contain some uncertainty. For example, what corrosion factor should I use for a given situation? Low resolution data acquisition in the field makes it difficult to pinpoint and understand torque fluctuations. However, by adjusting these parameters, you can match the rod string fatigue life with historical data for a given well. Again, somewhat iterative with some degree of uncertainty, but the module does provide insight into the effects of these critical fatigue-related parameters. The first example from the CFIR PC Pump Auxiliary Analysis module simulates a known pump size with an existing wellbore directional survey to produce the following graph of measured depth versus life for a given set of conditions. With a corrosion factor of 0.4, severe, and 10% torque fluctuations of the total operating torque, the minimum predicted fatigue life of the rod string is 324 days. I like to use the analogy of a horse race for fatigue crack propagation. In the area of highest dogleg severity, fatigue crack propagation happens the fastest. In areas with low DLS, fatigue crack propagation is slightly slower, but still progresses. Based on the above diagram, the first fatigue break, red, is horse number 1 to cross the finish line, while the other horses' fatigue cracks are not far behind. This results in more frequent breaks as a function of the dogleg severity and rod stress once the initial break occurs in a rod string. By preventing corrosion, you slow the crack initiation down, effectively preventing all horses from leaving the starting gate in the fatigue race. The second example utilizes the same pump size, operating parameters, and wellbore directional survey. In this case, only the corrosion factor is changed from 0.4 severe to 0.5 moderate, which, as you can see, has a significant effect on the minimum predicted fatigue life, now at 1,412 days, up from 324 days. On the next slide, I will show a comparison of the two measured depth versus life graphs. As you can see in the side-by-side comparison, note the change of scale on the y-axis from 100 to 100,000 on the left versus 1,000 to 100,000 on the right. CFR shows significant effects of corrosion in a deviated wellbore with both cyclic and torsional fluctuations. This is supported by our own internal testing, although the degree of influence is somewhat arbitrary and difficult to predict with absolute certainty. We know it has an effect. The effect and extent of corrosion in the oil and gas industry is far-reaching. We have now completed hundreds of installations in Canada and the US, primarily in PCP applications. Here is a summary of PCP installations currently sitting at 188, with insight into the current maximum run days and average run days by client, along with the total number of installations and average run days for all strings. Our digital web-based product tracking system has the capabilities of using geomapping coordinates tied to unique well identifiers to show installation coverage in the Western Canadian Sedimentary Basin, stretching from as far north in Alberta as Peace River to Swift Current and Estevan in the south of Saskatchewan. It can also be noted that we have completed one PCP installation with KeBond in the US, along with 44 reciprocating installations in the US, which are outside the scope of this presentation. Of the 188 strings installed to date, we have completed 82 surfacing operations on 42 different strings. Some of these wells have had multiple surfacing operations due to various pump or rod related issues. These strings were in good overall condition and either rerun or repaired and rerun according to established inspection procedures. Specific to strings that were surfaced and subsequently inspected, many were deemed to be in good reusable condition, with minor wear and little to no damage evident on our L1 field inspections. These strings were simply reused with some consideration for repositioning the string in the wellbore using sucker rod and pony rods to move the wear points up or down. Any strings with minor damage were repaired. This included mid-string rod breaks, pin end failures. Strings with measurable wear were either shortened by removing the worn KeBond section, repositioned to redistribute the wear points, or spliced with new rod as necessary to restore worn sections as needed. Regarding in-field repair, we have several methods of coating splice and pin end weld areas. On the left is an image of a mid-string elastomer repair sleeve after being in operation. It is slightly shinier than the KeBond and located inside the red box. These sleeves are molded and bonded onto the rod to cover welds at both the pin ends and mid-string splices. On the right are two images of our paint-on epoxy weld coating that provides excellent weld coverage during urgent field repairs. Both processes for string repair and splice coverage have been extensively tested and are actively being monitored in the field and during all inspections. Here are several examples of our Level 1 field inspection reports documenting the condition and disposition of a given rod string after surfacing it for inspection. These reports also include the reason for workover and comments from our field technicians on the overall condition after visual inspection of the rod. These reports are mainly observational and do not include high-level technical analysis for any strings that are typically repaired or rerun. 8 KeBond strings that have been surfaced were marked for further inspection or discard. These strings were returned to the field operation base for level 2 base inspection that ties string condition to meterage to categorize the extent of any damage recorded. These were then escalated to L3 engineering level inspections, which involve extensive analysis looking for root cause and contributing factors to the rod string failure. KeBond strings that have been discarded for one reason or another up to this point have undergone a higher level L3 engineering inspection that looks at digitally captured manufacturing data, QA/QC data, background and application information, operational history, review of the L1 field inspection, the L2 base inspection. These L3 inspections involve a high-level engineering analysis that includes visual, non-destructive, and destructive analysis work, followed by an analysis discussion section, and finally a summary and conclusion section. With significant installation momentum, we continue to monitor performance of both initial field trial product, along with more recently installed commercial product. The next section looks at the evolution of a few of these applications where we are tracking some promising results. The first sample well is focused in case study LSCS15 and involved corrosion-initiated fatigue in a directional well with 13.4 degree per 30 meter dogleg severity. The pump was landed at 892 MKB with 20 API oil gravity, 64% water, and 1% sand. This well experienced 13 rod-related workovers in a period of just over 2 years. The base runtime was established at 32 days based on historical rod string performance, while the target runtime was set at 180 days to prove economic success for our client. The base runtime improvement as of the middle of September 2024 was 11.8 times, with a target runtime improvement of 127% over the established KPI. This has resulted in an estimated savings of $89,000 based on significantly less rod repair work and 2 fewer rod replacements over this time period. Considering a $10,000 incremental cost for the coated rod string over the historical bare rod string, the estimated savings for this well is currently sitting at $217 per day. The second well is showing similarly positive metrics. With frequent corrosion-initiated fatigue failures, this well had a much lower 4.7 degree per 30 meter dogleg severity, with the pump landed at 850 MKB. The fluid emulsion consisted of 13 degree API fluid with 98% water and trace amounts of sand. Based on 25 rod-related workovers in the previous 2 years, this application is experiencing a base runtime improvement of 8.7 times, with a target runtime improvement of 143%, representing both a technical and economic success. Based on a $5,000 rod string repair cost and a $20,000 rod replacement cost, the estimated savings in this well are over $93,000, with an estimated savings of $320 per day. This real result continues to improve with one surface rerun inspection on this string, where it was redeployed after 133 days in operation and continues to operate after 292 days as of the time of this webinar. The next 3 slides contain a series of images from the same string in a single well that has been surfaced a total of 3 times. After 115 days in operation, the client experienced a broken sucker rod above the rotor. Observations after surfacing the string to replace this broken sucker rod included slight wear observed at 30-foot intervals corresponding to the line tubing joint connections, which can be slightly non-concentric on the ID once the tubing is threaded and coupled. There is also potential for the liner to be pinched if the line tubing connections are over-tightened. The clean section of the rod showed the original KeBond string skin, which was evident for the majority of the overall length. The same string was surfaced again after 230 days of total operation. It's important to point out that this well utilized line tubing. There was some wear concentrated at the tubing joint connections, indicative of slightly pinched tubing liner from over tightening of the tubing connections. This is a concern with used line tubing that is repeatedly coupled and decoupled, as the connections can be made up further and further over time due to wear on the thread profile. The final image on the right shows the telltale new rod skin in areas with little to no wear. The third time this string was surfaced, we identified more severe concentrated wear in the area of the tubing joint connections. This time there was a bottom pin failure on one of our proprietary IPC coated pin ends, right at the coating transition adjacent to the installed protective sleeve. A sample of the L1 field inspection is also included as an additional visualization. This string was repaired with the installation of a new bottom pin, and the string was repositioned slightly in the wellbore to redistribute the contact wear points with the tubing, and it's currently running after 417 total days of operation. So what have we learned thus far? Corrosive application success has led to 2 case studies, with numerous other cases seeing similar technical and economic success. Wear resistance is under investigation. The wear component is complex and involves variables from many contributors, including sand aggressiveness and concentration. Wellbore geometry, including consideration for dogleg severity, reverse curvature, and inherent rod and tubing side loading are also important factors. We have had wear-related failures, but we are also seeing success in applications where we were expecting wear. Lubricity of the produced fluid also plays a part. Oil is a lubricant, but will carry more sand due to the higher viscosity. Water is not a good lubricant, but with low viscosity, water does not carry sand well. Because the KeBond cannot be stripped, the opportunity is to strategically reposition the rod string in the wellbore during any servicing operation to move higher wear areas up or down to prolong the life of the rod string. This is similar to rotating the tires on a vehicle to extend tread life. Self-inflicted damage and defects during the sleeving preparation process on rod splices and pin end preparation were identified as an area of improvement, but reiterated the importance of preventing stress risers, for example pits and defects, on the bare rod string to improve fatigue life. KeBond has exhibited the ability to be flushed with hotter fluid up to 80 degrees C and does not become loose or spongy, which is a significant advantage over earlier generations of coated rod. Installation momentum continues with specific clients in specific fields, and we have significantly outlasted other coated product and are actively replacing sucker rod in strategic areas that are struggling with corrosion and corrosion-related fatigue failures. We also continue to evaluate coated sucker rod, bare sucker rod, and pin end coatings to further reduce failures by improving the accessory options for use with KeBond. At this point, we are going to open up the session for questions and discussion. I would like to thank everyone for attending, and I hope you found the information presented interesting and informative. Thank you. I think we're going to bring Lonnie and Chad on the screen here as well, and then if there are any questions from the participants, the method we're posting them into the chat group, and then in the back end we're going to bring those questions to the forefront and do our best to answer them for you. So if anybody has some questions, please post them in the group chat or the comments, and yeah, we'll go from there. Christopher Long just ran one of our strings this afternoon in Andrews County, Texas. Nice. Welcome, Christopher. I'm glad you were able to attend.
Nick Tumu, welcome, Nick. If corrosion is pressure dependent, would you consider coating the bottom half of the string only to save money? Yeah, Nick, that's a very good question. Not only is the corrosion pressure dependent, the corrosion acts with cyclic bending to create your your stress riser and then your cyclic bending fatigue. So in some cases we've considered, or not considered, we've actually coated the rod only from the 50 meters above the kickoff point down into the areas that are experiencing cyclic bending. And if that's where your corrosion is happening, yeah, we can definitely do hybrid strings where it's the top half is bare and the bottom half is coated. So absolutely, if that's if you're only seeing corrosion at the bottom of the string and you've got cyclic bending in that area because it's a horizontal well, absolutely. Thanks for the question, Nick. Christopher Long, definitely appreciate that feedback. It's sometimes difficult when those jobs are happening down in the US. It's a long ways away from where this stuff is manufactured, but it's good to get that feedback, so appreciate that. Jamie Ross, what is the longest string installed so far? So in PCP applications in Canada, our longest string down in the Swift Current area is just over 1,400 meters long. So that's about, for anybody in the US, that's 4,700 feet. The string weight there was about 6,200 kilograms or 13,000 pounds. We've gone much deeper than that in reciprocating applications in the US. Some 1-inch 7/8 tapered strings that are encroaching on 2,500 meters, 8,400 feet, 10,000 kgs, 2,200 pounds. So our service rating for installation of this stuff is 20,000 pounds. So we're right in that area. Even we've done a couple strings that are slightly heavier than where we're rating this stuff at. So that answers that. Christopher Long, very interactive. I like it. What is the highest deviation that you have ever run the KeBond? So in a lot of our testing, we had put a rating on this stuff to kind of be able to handle that 12 degree per 30 meter, which is about 12 degree per 100 feet. We had the one installation where it's 13.4 degree per 30 meter. We're actively trying to evaluate dogleg severity versus the side loading and then versus the wear component. We have very good wearability with oil and with water. In the presence of sand, some of those higher deviations could become a problem. So yeah, I would say 12 to 13 degree per 30 meter is kind of where we're sitting. Ooh, gripper modifications required to handle availability. This is a great question for our fleet manager, Chad.
Yeah, you bet. Yeah, good question. So yeah, gripper modifications, it varies. We've tested different grippers, different pads. I'll share some of this testing was right from small lab scale to trialing on a test well and then field trials. So have a pretty good idea what works, what doesn't. What I'll say here is there's certain grippers out there that are good to go, and then others that might need different pads so it doesn't damage the KeBond. And then I find there are certain models, kind of one-offs, maybe they're a bit small, the skate length is real short, and certain models don't work well. So I'll leave it at that. But really, it comes down to gripper pad, contact area. Some work well right out of the box. Others don't.
I think I could add maybe a little bit to that too. We're actively working, internally with our own fleet of service equipment. We're also actively working with the third-party providers to evaluate their equipment, to evaluate the pads that they have in service, and provide them with recommendations to bring their fleet up to service quality requirements that we have for, all the way from safety to gripper pad blocks to, rod support clamps, fishing tools, all that stuff. So Chad and his team have put together a lot of that information, and we're actively working with anybody who's actively servicing continuous or endless rod out there to get them up to speed so that they can service this coated rod.
Yeah, that's right.
More questions? There's got to be some. We got to have a hard question for Lonnie. He's just sitting back all comfortable there right now. Richard Park, are you primarily focused on corrosion prevention, or are you installing KeBond strings in applications to reduce wear? Yeah, we are primarily focused on corrosion prevention. We are really evaluating, I talked about this in one of the slides, we're really evaluating KeBond in wear applications. We find that sand tends to be very aggressive with the plastic or the polyketone coatings. Sand can get embedded in line tubing. Sand can get embedded in these coatings, and you can see some higher wear rates there. So we do have lots of applications in wear applications where we're expecting some wear, and the KeBond seems to last good. We've done a lot of internal testing as well with different conditions between bare rod, KeBond, line tubing, bare tubing, with water, with sand, and kind of evaluating those wear rates to put a little bit of science behind what we're doing there. But it is primarily focused on corrosion pit prevention, which is a massive contributor to rod string fatigue. But we're actively evaluating this in wear applications. It's just very complex, all the variables involved in evaluating this stuff from a wear perspective. What else we got? I think this is a good question here for our engineering team. Is there a difference in the friction between the rod and tubing with KeBond versus bare rod? Lonnie, you want to take that one?
Yep, sure can. We are and we're continuing to evaluate friction using, we have a laboratory rotary wear test equipment, and it simulates PC pumping, and it comes with a highly sensitive torque cell where we can measure the frictional resistance between the rotating rod and the tubing, and then we convert that back to a friction coefficient. And we've done comparative testing between bare and coated endless rod against both J55 and HDP line tubing with a variety of contact loads and various fluids, oil, water mixtures, and solids. So in pure water, kind of the simplest case with bare rod rotating against J55 tubing, we measured friction coefficients of about 0.3. And then when we run that bare rod against HDP line tubing, we see that value decrease to about 0.2. Now with the coated rod, whether it be the EthiFlex or the KeBond, the friction coefficients of the water decreased to between about 0.1 and 0.15 with both steel and the line tubing. So we didn't see big differences between the two. So that's about half of what we measured on the bare rod and J55 tubing. As we put solids in there, we see the friction factors increase slightly, and when we put oil in there, we see them decrease slightly. We're also attempting to evaluate the friction coefficients out in the field from the drive head torque measurements, but it's difficult to reliably separate the friction contributions from the rod string and the pump. Right, the pump can have a lot of friction, and understanding what's driving that can be difficult. And then I know this is a PCP focused webinar, but on the reciprocating side, we're trying to get the surface load data and then look at friction from that standpoint as well.
Is KeBond compatible with line tubing? We've kind of talked about this. I mean, Lonnie's hinted on a lot of the wear testing that we've done. I talked a little bit about it in the previous question, but the answer is yes. There are some complexities in line tubing with abrasives. Abrasives are really, I think the biggest concern here. Like, I would almost reword that question: is KeBond compatible with sand and abrasives? In some cases, the sand and the abrasives can get embedded in line tubing and can get embedded in the coated rod. So we need to be fairly careful evaluating applications with high sand concentrations. We have many strings running in applications with line tubing with high water cut, decent oil film, and they're lasting a significant amount of time. So we are not necessarily concerned with KeBond compatibility in line tubing. So what else do we have from internet land here? Is there any other questions from the crowd? I see 17 people kind of hanging on here. There must be one or two more questions. We'll try to wrap this up, I guess, in the next couple minutes. So Avery, can KeBond be fished if the rod parts? Hey, that's a very good question. That's a good concern. A lot of our clients ask, and I think I'll turn that one over to Chad to talk about a lot of the testing and certification that we did for some of the fishing tools.
Yeah, what we found was so tested a couple common brands in the lab, and they both worked well. And even since then, I've heard in the field that our field crews are trying other brands as well, and they work well. So with fishing tools, it's not that it's a custom, only one works. What we found is, and to be honest, we thought from our lab testing that it would be a 2-run process. So first run, you're nipping 4 to 6 inches of coating off, clean out the tool, or put a smaller size. Second run, you're latching onto bare rod. But what I've heard from the field service team is they've never had to double run. It's always latches the first time. So really, we do have specified brands, but we're finding that there are tools that work that we haven't even tested, and they do work. So really not a concern there. You just got to latch onto that bare rod and it'll pull it.
Okay, we're coming up on about 42 minutes here, so I think we probably cut this off around 45 minutes. But Lifting Solutions team in the background. Any more questions coming in through the comments? What are the specific handling tools required to service KeBond? I think another question here that we can direct at Chad. I know,
Yep.
We call it a servicing kit, but I think we'll let you describe what's all in there.
Yeah, I'll expand off of the, earlier question was specific to the gripper. So that's the main component, but the other handling tools or equipment would be the rod safety, in case of a runaway, rod clamp, and then fishing tools. And so fishing tools isn't anything unique or specific, but we have listed what we found works well. The rod clamp is a specific custom clamp. It's really a modified clamp, different inserts for different rod sizes. So it is size specific, but you just swap out inserts. And we have a clamp that we've developed, and then the other would be the rod safety. And this one, I mean, we have had limited success with the existing safeties that come on typical rod servicing equipment. And so we've developed a rod safety that we've proven to have 100% success. And that's kind of a standalone safety, sets on top of your existing stack. You could thread it into your existing stack, runs off chassis or truck air pressure. And so if you're running KeBond and you want 100% confidence, there's this the safety that we recommend. So those are really the four. I'll say four. It's the gripper, specifically the gripper pads, the safety, clamp, and fishing tools. Those are really the specific handling tools and equipment.
Yeah, perfect. I think that's important when we start looking at some of the deeper strings that we've been installing, in the reciprocating applications in the US. So I think, to kind of close this off, our next webinar that we're planning is going to be, in Q3 here, maybe, or Q4, sorry, around the end of October. It's going to be RRP focused webinar where we're going to be joined by the guys from the US that have been really, kind of pushing the limits on depths and temperatures and in these reciprocating applications in the Permian. So stay tuned to our social media for, some upcoming information on that. And for the 10 of you that are left kind of watching, appreciate everybody joining us today. And I think at this point, we're going to sign off. So thanks, everyone.